I now want to talk more about this standard enthalpy of reaction. So I want to talk more about how we could calculate it. Calculating this value right here. And so, like in the previous example, what we did, or your standard enthalpy of reaction, for many different types of reactions, they're just going to be listed in various tables out there. And so this standard delta HR for many reactions are just tabulated. For example, if you look in the Chemical Engineering Bible of Perry's Handbook, you'll see that they list a lot of different delta HRs. Now, this value, or the enthalpy change of a reaction just in general, can also be measured, obviously. And they typically do it by using a device known as a calorimeter. You measured in a calorimeter. We won't go into too much detail about this. All you need to know is that it exists. Now, other than measurement, or other than looking it up, we could also determine what the standard delta HR of a reaction is, and we could do that indirectly. And so, in this video, or the next set of videos, I want to talk about different techniques we could use in order to calculate what the standard enthalpy of reaction is for a reaction. And so to start this off, the first thing I want to talk about is something called Hess's Law. Now, you may be familiar with Hess's Law. You may have talked about it a little bit in your General Chemistry 2 course. But basically, Hess's Law is an important theorem that allows us, or enables us, to calculate our standard enthalpy of reaction indirectly. Okay? And so what this theorem states is that if you have different chemical reactions, and if you add the chemical formula for these chemical reactions together, what you're going to get is an overall reaction. And so the addition of chemical equations leads to an overall equation. And so because of this, that means if you add the delta HR of different chemical equations together, then the delta HR of your overall equation is just going to be a sum of those delta HRs for each equation leads to an overall delta HR. And the reason this works goes back to what we discussed when we first started talking about internal energy and enthalpy. And this principle works because enthalpy is a state variable. Okay, let's now get some practice putting this law or this theorem into practice. And so let's start with this example. Let's say we have a series of 3 different reactions, where reaction 1 involves 1 mole of carbon reacts with oxygen gas to form CO2, and that the standard enthalpy of reaction for this reaction is this value. For reaction 2, what we have is a mole of carbon monoxide reacts with half a mole of O2 gas to form CO2 as well. And the standard enthalpy for this reaction is also known. Alright, let's now take this a third reaction, which involves 1 mole of carbon plus half a mole of oxygen, and that forms carbon monoxide. And what we want to figure out is what's the standard enthalpy of this reaction. Let's say it's unknown. Okay? And so to figure out the standard enthalpy of reaction for reaction 3, we're going to use the data we have for reactions 1 and 2. Okay? And so the first thing we need to figure out is how do we get an overall reaction 3 from reactions 1 and 2. So how do we get reaction 3 from reactions 1 and 2? Okay? And so I'm going to write reaction 3 over here again. I'm going to write it just like we wrote it before. And so what we have is we have a carbon on the left-hand side, an oxygen on the left-hand side, and we also have a carbon monoxide. All right? I'm now going to draw a straight line here. Doesn't need to be blue, so go back to black. Okay? And now what I want to do is I want to figure out how I could take reactions 1 and 2 and how I could add them together in order to get reaction 3. Alright? And so here I'm just going to rewrite. If I take a look at reaction 1, I see that it also has a carbon on the left-hand side. Right? And also an oxygen on the left-hand side. So I'm just going to rewrite it here. Alright? Now, for equation 2, what I see is that it has a carbon monoxide in the equation, but it's on the left-hand side, right here. Alright? And so, but in equation 3, I want it on the right-hand side. And so what I'm going to do is I'm actually going to write the negative of reaction 2 here. I'm going to take the negative, and if we apply a negative sign to reaction 2, what we do is we flip it. So everything switches sides. And so now what we have is carbon dioxide, CO2, 1 mole of that forms 1 mole of carbon monoxide and half a mole of O2. Okay? And so here are these two reactions, and what I want to do now is I want to add them together. So I'll put a plus sign here. Alright? And when we're treating chemical reactions like an algebraic equation, what we have to remember is that if things are on the same side, if a species is on the same side, we add them together. And if a species appears on opposite sides, what we do is we subtract them. Okay? And so when we add this reaction 1 and the negative of reaction 2 together, what we see is that we have oxygens on both the left and the right hand side, and we also have CO2 on the right and the left hand side. And so when we add this reaction together, what's going to happen is we're going to end up with a carbon, and then we have 1 mole of oxygen or O2 on the left hand side and half a mole on the right hand side. So if we subtract those from each other, we get 1/2 mole of O2. And then we see that we have 1 mole of CO2 on the right hand side and 1 mole of CO2 on the left hand side, and so those completely cancel out. Alright? And then we also see that we have 1 mole of carbon monoxide on the right hand side. So if we add those things together, we see we get 1 mole of carbon plus 1/2 mole of O2 yields carbon monoxide, which is exactly what our equation 3 is. And so by doing this, we calculated an overall reaction. Alright, so the operation we did is we took equation 1 and then we added the negative of delta HR2 to it. Alright? And so, in order to calculate the standard enthalpy of reaction for reaction 3, what we're going to do is the same sort of operation, but we're now going to do it on the delta H of R's. So if I go to a new page, what we're going to do is the same operation. Same operation with delta HR. So our delta H, our standard delta HR of 3 is going to be equal to our standard delta HR for reaction 1 plus the negative of the standard enthalpy of reaction for reaction 2. And so if we add those values together, so plus the negative of something that's already a negative, what we get is that the standard enthalpy of reaction is equal to negative 110.5 kilojoules for reaction 3.